Hi, Assalamualaikum. My name is Nur Atira binti Wan Ismail. You all can call me Atira, and I was first presenter.
Hi, Assalamualaikum. My name is Siti Najiha binti Makjaman. You can call me Najiha, and I was the second presenter. Okay, thank you.
As you can see, question 1, number 6, the set of integer p has no proper non-trivial subgroup if p is a prime number. That the questions. So I would like to explain how to prove the questions. Firstly, suppose h is a non-trivial subgroup of the set of integer p. Since the set of integer p is cyclic, so h must cyclic. Why h must cyclic? Because based on theorem 6.6, a subgroup of a cyclic group is cyclic. That's why h must cyclic. For the next slide, I would like to continue my proof. Suppose h equal to cyclic group generated by b, but b equal to b1. Since p is prime, the order of b is p over GCD BP equal to p over 1 equal to p. Therefore, only subgroup of integer p are h equal to element of 0 or h equal to integer p. That is, integer p has no proper trivial subgroup. For example, suppose that G is a group with more than one element and G has no proper non-trivial subgroup. Prove that order of G is prime. So for the solution in this question, I will share with you. Let order of G more than equal possible order of T equal to infinity. If G has no proper non-trivial subgroup, then G and cyclic group of identity are the only subgroup. Let A element in G be a non-identity element. Then, the subgroup generated by A cannot be cyclic group generated by identity. So, cyclic group generated by A equal to G. Hence, G is cyclic. If order of G equal to infinity, then G approximately equal to integer. But integer has non-trivial proper subgroup. Thus, order of G less than infinity. Suppose order of G equal to n. Since G is cyclic, for every divisor D of n, there exists a subgroup H of order D. If D is not equal to 1 or D not equal to n, then H is a proper non-trivial subgroup of G. Therefore, the only divisor of n are n and 1. Hence, n is prime. That's all for me, so I will pass to the next presenter, Siti Najiha.
Okay, thank you, Atira. So, I would like to continue the presentation for the next question, question 2, number 2. Okay, the question is, if M divides the order of a finite abelian group G, then G has a subgroup of order M. Okay, in order to prove this statement, we use the theorem 9.12 and 6.15. Okay, first, by theorem 9.12, we can think of G as being the integer of P1 R1 times integer of P2 R2 times until integer of Pn Rn, where not all primes Pi need be distinct. Since P1 R1, P2 R2 until Pn Rn is the order of G, then M must be of the form P1 S1, P2 S2 until Pn Sn, where Si is greater than or equal to 0 and smaller than or equal to Ri. Okay, next, by theorem 6.15, okay, Pi Ri minus Si generates a cyclic subgroup of integer of Pi Ri of order equal to quotient of Pi Ri by the GCD of Pi R and Pi Ri minus Si. But the GCD of Pi Ri and Pi Ri minus Si is Pi Ri minus Si. Thus, Pi Ri minus Si generates a cyclic subgroup of integer of Pi Ri of order Pi Ri divided by Pi Ri minus Si equal to Pi Si. Okay, recalling that A denotes the cyclic subgroup generated by A. We see that P1 R1 minus S1 times P2 R2 minus S2 times until Pn Rn minus Sn is the required subgroup of order M. Okay, next, lastly for the example, for this question, if M is a square-free integer, that is, M is not divisible by the square of any integer and greater than or equal to 2, then every abelian group of order M is cyclic. So in order to prove this statement, let G be a finite abelian group of square-free order M. Then by theorem 9.14, G is isomorphic to the integer of D1 times integer of D2 times until integer of Dk, where each Di is greater than or equal to 2 divides Di plus 1 for I greater than or equal to 1 and smaller than or equal to K minus 1. So the order of G is M is equal to D1 times D2 until Dk. Okay. So if K is greater than or equal to 2, then D1 power of 2 divides M, which is a contradiction. Thus, K is equal to 1 and G is cyclic. So that's all from us. Thank you everyone and thank you sir.